Hello, good morning, everybody. I'm Matilde Barberi Squarotti, and I'm beginning the third year of my PhD in Milan. And today I will talk to you about measuring the neutral hydrogen, the power spectrum of neutral hydrogen with MeerKALSS telescope. Neutral hydrogen is a very powerful probe for cosmology because it traces the dark matter distribution for a wide range of redshift, even more extended than what we can do with galaxies. And its amplitude, the amplitude of the signal, which is due to the hyperfine emission at 21 centimeter, depends on the clustering of H1 in the universe. And so we can measure its emission to probe the three-dimensional structure of the universe. However, the big problem that until now prevented any detection in autocorrelation is that at 21 centimeter, we don't only have a cosmological signal, but we have strong foregrounds, in particular galactic foregrounds that are orders of magnitude more powerful and stronger than the cosmological signal in all the frequency band that we want to use for cosmology, but also contaminants like radio frequency interferences, instrumental contamination that are very hard to remove from our data. Despite that, quite big observational effort is ongoing also to get ready for big experiments like the SKA observatory. And one example is the MeerKALSS telescope, which consists of 64 dishes in South Africa. And in particular, I will be talking about the effort of the MeerKLASS collaboration that is performing large area surveys in the Southern Hemisphere, of course. And in particular, I will talk about the deep survey that was performed in 2021. This survey consists in a total of 62 hours, covering a little bit more than 200 square degrees in the sky. And the effective redshift of this survey is roughly 0.4. How this survey was conducted, we were using the single dish technique, which means that all the 64 dishes were pointing towards the same region at the same moment to reach a higher signal to noise ratio in a faster, in a quicker way. And the same patch was observed multiple times, again, to improve the signal to noise ratio. Then how the calibrated map is then built by combining all the observations that were performed at different times and by different dishes, and to get a final calibrated map. And a way to analyze this data, instead of combining all the observational blocks in a single subset, is instead to build independent subsets from the same observational campaign. And even though by doing this, we of course lose some signal to noise because we are building smaller subsets, this can be a very powerful way to get rid or at least to mitigate some of the systematics that affect our data. And in particular, if you then measure the cross correlation between subsets, you don't have the thermal noise contribution in the power spectrum, and also the independent systematics that might still affect the data should be mitigated. In particular, we tried to optimize the definition of this subset by looking at the signal to noise ratio, and we ended up with this sort of chessboard division where we have four subsets, A, B, C, and D, that we can then cross-correlate together. Of course, having different subsets don't cancel all the foregrounds. So for that, we, again, have to apply some foreground cleaning. And to do this, we use blind methods, basically principal component analysis. But to be more accurate, we decided to, first of all, filter our map with some wavelet filtering in order to get a coarse and fine scale version of our map. On these maps, it's way more effective to identify the principal components, and therefore we can perform the cleaning independently on these large and small scale maps. Then afterwards can be added back together to get the final cleaned maps. And this technique is actually not new. Also in MeerKLASS, it was already adopted for a previous data set and was overperforming the standard PCA. Now, with the clean maps, we are ready to compute all the possible cross correlations between subsets. So, of course, you have to transform the to do a coordinate transformation to go to a Cartesian box, and then we have a narrow scale range going between roughly 0.1 to 0.25 h over megaparsec. We have 9 k-bins in a scale range that was tailored to also exclude some regions that we know can still be affected by signal loss or potential residual contaminants. And with this cross power spectra, of course, we can't perform an independent analysis on all of them, because otherwise we would end up with multiple results from the same data set. And therefore, we adapt the multi-tracer formalism to our multi-subset case, because in the end, all our subsets are tracing the same underlying matter distribution. And we only focus on the cross power spectra, and we discard the auto power spectra, because those are still noise dominated and wouldn't give additional information to our analysis. Another conservative choice was actually to focus only on the most independent subsets that we have. So for example, we only include in our data set the PBD power spectrum and the PAC power spectrum, because those ones are built with observational blocks that were observed in different times and by different dishes. And we build a jackknife covariance for the full data set. We don't want to constrain any cosmology yet with this data set, but just to have a measurement of the cosmological signal from H1. And therefore, our only physical free parameter is the amplitude of the power spectrum that we parameterize by the product of the H1 abundance and its linear bias at the redshift of interest. And we also include a nuisance parameter for each cross power spectrum, because we know that after the foreground cleaning, we might have some signal loss in the data due to the coupling between foregrounds and the cosmological signal. And we then perform multi-parametric fit to constrain these parameters. And what we get is really promising, and we are very excited about these results, because we can get very good fits characterized by reduced chi-square of roughly 1, and with a high signal to noise ratio above 10. And we also performed a variety of consistency checks and robustness tests to rule out and be sure that we are not contaminated by residual systematics in the cross correlations. And another promising outcome is that we find an agreement also with previous results obtained both with previous surveys of the MeerKLASS collaboration, but also from the same data set analyzed in cross correlation with an external galaxy survey. And with these results in mind, I can leave you with my conclusion, which is, of course, 21 centimeter intensity mapping is a great probe for cosmology. And within the MeerKLASS collaboration, there is a very big effort to make this possible, also paving the way for bigger experiments such the SKAO that should start in like late 20s, beginning of 2030. And this is actually the first direct measurement of the H1 cosmological signal independently from any other external catalog. So it's really nice. And I will be happy to take your questions, even in the coffee breaks or whenever you want. I don't remember disease consistency. Of course, the cross correlation measurement is has a slightly lower value of omega H1 BH1, but it's still within like the uncertainties of the fits. It's so I wouldn't I'm not aware of the inconsistency.